Hey guys, welcome to lecture number 20. So just like I said yesterday, in this lecture, we will be talking about optimization in physical sciences and engineering, and perhaps we can even go beyond that and we can see some optimization problems in economics and why not business. Well, this would be the last lecture from chapter number 4. And this will conclude everything about the derivatives. So as you have noticed so far, we've talked about in chapter 3 about the derivatives, more about quantitative properties of the derivatives. And in chapter number 4, we talked about additional properties of the derivatives. And we dwell more on qualitative properties of derivatives. Okay. So let's get started. So let me start with something what we will call optimization procedure. Okay. So optimization procedure. And I would like to give you more or less some steps that you should follow when you deal with an optimization problem. And well, we will have the following. So step 1 is to draw a figure and label all quantities relevant to the problem, and label all quantities relevant to the problem. Step 2, now we focus on the quantity that we want to optimize. So focus on the quantity to be optimized. And I will explain immediately. What do we mean by that? Well, we would like to name it. And we would like to find a formula for the quantity to be maximized or minimized. Quantity to be maximized or minimized. Or minimized. Okay. All right, so that's step 2. On step 3, in step 3, we would like to use the conditions from the in the problem to eliminate variables in order to express, and we like to express the quantities in terms of a single variable. So because you will see that we'll have more variables, and once we know some relationships between the variables, then we can express everything in just of one single variable, which is exactly what we want to do. All right, so let's write this. So we will use conditions in the problem. To eliminate variables in order to express the quantity to be maximized or minimized. And this is important. So we would like to express this quantity in terms of a single variable, in terms of a single variable. This is important. Okay. Now step 4. Right, once we get rid of all those variables and we have only one variable, right? We would like to find the practical domain. So the practical domain for the variables in step 3. In step 3. Okay. And now the last step, step 5, what we would like to do here is, if possible, use the methods of calculus and, well, when I say the methods of calculus, I mean qualitative properties of the derivative, and you will see in examples. So we'd like to use these methods of calculus to obtain the required optimum value. Optimal value. Okay, so these are the steps. I want you to look at them. And now we will work these 5 steps through some examples. And like I said, I will insist on examples in economy, in physical sciences, engineering, whatever. And now let me start with the first example. So once again, look very carefully at these methods. All right, now let's see the first example. So example 1. In this example, we would like to model, so it's about modeling. It's a modeling problem, maximizing a constraint area. A constraint area. All right. So what we need to do is the following. So we need to build, so a rectangular fence to enclose a play zone for children. Now we're asked, what is the maximum area? So this is important for display if it is to fit into a right triangular in fact, let me write it again, into a right triangular, right? plot with sides measuring 4 meters and 12 meters. Okay, now let's look at the problem. Let's read it carefully. And now we would like to draw a picture so that we can see better. So we want to build a rectangular fence to enclose a play zone for children. What is the maximum area for this play if it is to fit into a right triangular plot? Oh, this is important here. With size measuring 4 meters and 12 meters. All right, let's draw the picture then. In fact, I will just draw it here. I have this. So this is the right triangular plot. Now let's just say here we have A, here we have B, here we have C, right? And here we have this rectangular, so C, let's say here we have D, C, E, and here we have F. Okay, and this is the area. See here. So this is what we're interested in. All right, and what do we know? So we know that the distance from here to here, it's 4. So this is 4 meters, and the distance from here to here, this is 12 meters. All right, that's great. Then the distance from here to here, it will be, let's say, and from here to here will be, this is an X, and this is here a Y, right? And now let's, what we're interested in is to find the area of the play zone. So let's write this. So the area of the play zone is nothing else than just, well, let's call this by A. So A will be the area of the play zone, and this is nothing else than just X times Y, right? Is the area of the rectangle, BDEC, right? And the area is X times Y. Okay. And now let's look carefully here, right? Because we would like to use something in geometry. And we would like to look at these two triangles, the triangle ABC. So let's look at this guy here. Right? And ADF. And also let's look at this guy here. So ADF. So we want to look at this guy as well. Well, what can you tell me about these two triangles if you look at them? Well, they're kind of similar. So the corresponding sides, well, they're corresponding triangles, if you want to put it like this. So their corresponding sides are proportional. So the triangles, let's write it like this, triangles ABC and ADF are corresponding triangles. Okay, great. So this implies that their corresponding sides sides are proportional. This is very important to know. So this means that AB over AD is the same as, so AB over AD is the same as BC over DF. So AB over AD, so this ratio is the same as BC over DF, and it's the same as AC over AF, right? So we know this because these two triangles are similar or corresponding, whatever you want to call them. All right, that's great. Now let's see, what do we know about this? So let's look at this equality here. AB, the first two. So AB over AD is the same as BC over DF. So what do we know? So also we know that AB is, if we look at the picture, look here, it's 4 minus y, and BC will be x. So let's write all of them. AD is 4, and DF is 12. All right. So from this ratio, this implies that, so from AB over AD equals, so the ratio that is circled in red will imply that, so that 4 minus y, everything over 4, is the same as x over 12. All right, that's beautiful. And from here, if we do the computations, this will imply, so 3, okay, so this will imply that y is the same as 4 minus 1/3 times x. So we get this equation. So we can write y in terms of x in this way. Okay. Now, if we multiply by x, so which gives us, if we multiply by x, so this will give us xy, right, is the same as 4x minus 1/3 x squared, right? So note that the problem had initially 2 variables, but now it has only 1 variable. So note that we have only a single variable. Right? So at this point, we can consider this function. So we can look at this guy here, and we can consider this as a function of, let's say, a of x, area of x. Right? So what we need to do right now, so consider the function a of x to be 4x minus 1/3 x squared, and a is defined. Now let's see for which values x is defined. For this is defined for all values of x between 0 and 12. So this is 0, 12, and real value function. All right, that's great. So that is the domain of a of x. And now what we need to find, so we need to find the maximum area of the play zone. So that's what we need to find. When the area of the play zone is maximum. So in other words, we need to find the maximum value. So in other words, we need to find the maximum value of the function a of x, right? So that's what we need to do. Okay, that's great. So let's do it. So now, as you can see, I have this is a quadratic function. So I have to compute the derivative. So the derivative of a of x is given by a prime of x equals 4 minus 2/3 times x. Okay, now the critical numbers. So the critical numbers we obtain them when we set the a prime of x equal to 0, and this will be equivalent with 4 minus 2/3 times x is 0, and this will give us, this will be equivalent with x equals 6. Okay, so that's the critical number, x equals 6. And now the critical point is given, so we have to compute a of 6, which will give us 12. So this point of coordinates 6, 12 is a critical point. Okay, so we have this at this point. So we see we have exactly at when this minimum or maximum is obtained. So let's see. Now we want to find, so we find the maximum area. That's what we do. And we know that a of 0 is 0. A of 6 is 12. A of 12 is 0. So the maximum area will be 12. So is 12. When is it attained? When at 6, when x equals 6. So in other words, we can have the following picture. Let me draw it. So it will be maximum when we have here 2, and here we have 6. This will be the maximum. So this is when the area is maximum. Okay, right? So this is what you do. You just use calculus to do this. So now you see, let me recall. How do we find the absolute maximum? So first, we need to find the critical numbers, first order critical numbers. Then, secondly, we have to identify the endpoints of the domain, as you have seen here in the case of this function. So the endpoints are 0 and 12, and we evaluated our function at those 2 points, right? Then we need to evaluate exactly that function at the endpoints, but also the critical number, right? And then the maximum found in the previous step is the maximum of the function, and we call this the absolute maximum. That's what it is, right? I think this picture is pretty clear at this point, right? But it was a bit tricky problem. Now let me give you another one. So now we have seen how we maximize the area, but now we will try to maximize a volume. Oh, okay, example 2. There will be a bunch of examples. And now, let's say the following scenario. A carpenter wants to make an open top box right out of a rectangular sheet. Of 24 inches, right? Um, 24 inches wide and 45 inches long. Okay, let's keep this in two numbers in mind, wide and long. Okay, the carpenter plans to cut congruent squares out of each corner of sheet. And then bend bend and solder the edges right of the sheet upward right, okay, to form the sides of the box. Okay, now we're asked for what dimensions does the box have the greatest possible volume. Okay, this is so we would like to see what dimension the box have the greatest possible volume. All right, look at the statement again. Let me look, I think it's correct in my notes. Yep. And now let's draw a picture so that everything will be clear. I think if we draw the picture, everything will be clear. So I'm going to draw a big one. Right? And here we will have okay, right? So this will be, this is X here, right? X, the same goes here. All right, and now this guy here, from from here to here, we said that this is 24, right? And this guy from here to here, it's 45. So we said this, right? The same goes with the parallel sides. Okay. Now it's quite clear what happens. Let me look here. This guy here from here to here, so between these 2 points, so let me point them out here so that you can see it. So from here to here, this will be 24 minus 2x. From here to here, this will be 45 minus 2x. And again, from here, the same goes here. And the same here. So this is 24 minus 2x. This is 45 minus 2x. Okay, so we have this picture, right? Look at it. And now we would like to, so x is nothing else. So let me write here. So x is the height of the box. Right? And this 24 minus 2x is nothing else than just the width of the box. Okay. And here we have this 45 minus 2x is nothing else than just the length of the box. Right. All right, and at this point, so we know that, so this is a parallelepiped. So the volume of the box we know is the base times the height, right? And times the other length of the side. So the volume of the box is, let's call this v of x, and we can express this in terms of one variable function, which is great, right? So we can write this as this is x times 24 minus 2x and times 45 minus 2x. So we need to find the dimensions for which, look at the question. So for what dimension does this box have the greatest possible volume? So in other words, we need to maximize the volume function. So in this case, we would like to obtain the maximum value. So we want to obtain the maximum value. That's what we want to do. Okay. So what, keep in mind that this is the function, as you can see it, v of x is x times 24 minus 2x times 45 minus 2x. Okay. Now, again, at this point, this is just a calculus problem, so we would like to just to take the derivative of this. So the derivative, v prime of x, well, it's a product. You can, okay, if you multiply, let me multiply all this. So this is, if you multiply this, this would give us nothing else than just 4x cubed minus 138x squared plus 1080x. Yeah, according to the notes, this is what it's this. And now the derivative. Now v prime of x is nothing else than just 12x squared minus 276x plus 1080. And now we can factor this. We can factor a 12 here. So it's 12 times x squared minus 23x plus 90. Right? Yeah. Or if you want, you can go for, let's go further and look at this expression. So this would be equal to 12. Okay, let's do it slowly. So we have that this is, let's break this 23. So it's x squared minus 18x minus 5x plus 90. So this would be 12 times x minus 18 minus 5 times x minus 18. Okay, that's beautiful. And now we can factor things in a nice way here. So this is x 12 times x minus 18 times x minus 5. So this is the derivative. And now we'd like to find the critical numbers. So the critical numbers are given by those points x for which v prime of x is 0. So this would be, will imply that x is 18 and x is 5. But you see, we have to see from how is our function defined. We forgot to say this. So we forgot to say how the function is defined. This is very important. The function is defined from 0 to 12. Pay attention. And the real value. This is important here. Very important, the way it's defined. But you see, 18 is not in the domain. This is not, okay, let me write it like this. This is not in the domain 0, 12. So it's not good. So this is the only one that's good. So the only critical number is this x equals 5. So the only critical number is x equals 5. All right, and now just like I said, we evaluate the function at the endpoints on the interval at which is defined. So at 0 and 12. So now we have v of 0 is 0. V of 12 is 0, and now we want to evaluate v of 5. And v of 5, if we evaluate this, just look at the function. So it's 5 times 24 minus 10 times 45 minus 10. Oh my. And this would be 5 times 14 times 35. Which is, let me look, 2450. So the maximum volume is 2,450 inches cubed. And the length of the box is, 45 minus 2x, which will be 35 inches. The width, that was the word I was looking for. So the volume is the length times the width times the height. So the width of the box is 24 minus 2x, so it will be 14 inches. And the height of the box is 5 inches. As you can see, when you multiply these three numbers, you will get exactly this here, 2,450. Right? Okay. I think you got the gist of these two applications. Now, I would like to see, let me see, maybe one more in business. Yeah, I would like to do one more application in business, probably I'll stop. There are plenty of others. Maybe I'll do some others, the review session, one we'll have for the final exam. Now let's talk about optimization in business. So example 3. We'd like to see optimization in business. Okay. So we like to maximize our the profit of our business. And let me take the following example. So this is a very classical one. A manufacturer can produce a pair of earrings at a cost of $3. The other way around, right? The earrings have been selling for the earrings have been selling for $5 per pair. And at this price, consumers have been buying 4,000 pairs per month. Have been buying 4,000 pairs per month. Okay, that's good. So now the manufacturer is planning to raise the price of the price of the earrings right? And estimates that that for each $1 increase in the price, uh, 400 fewer pairs of earrings will be sold each month. Okay, now we're asked at what price should the manufacturer sell the earrings to maximize the profit? The earrings to maximize the profit. Okay, this is a pretty real world application, in fact. So let's read it carefully. So a manufacturer can produce a pair of earrings at a cost of $3, okay? And the earrings have been so the earrings have been selling for $5 per pair, and at this price, consumers have been buying 4,000 pairs per month. So the manufacturer is planning to raise the price of the earrings and estimates that for each dollar increase in the price, this is important information. So for each dollar increase in the price, 400 fewer pairs of earrings will be sold. Not solved. Jesus, yeah, it's kind of late in the night, so I have. You'll excuse me for that. Will be sold each month. So at what price should the manufacturer sell the earrings to maximize the profit? Wow, this is like a business. All right, let's see. So we want to maximize our profit, but we have to keep something in mind of the profit. Let's just say that. So first, I want you to look again at the statement and now let's see. Now we'll consider let x, so we'll consider a variable x denote the number of $1 price increases. So x will be non-negative, that's clear. And we're going to denote now, we know that this p of x function, we're going to, this will be the profit. And we also know that the profit is clear, that is the revenue minus the cost. This is important. All right, and let's see what the revenue is. And let's see what the cost is. So the revenue will be the number of pairs sold, price per pair. So this is the number of pairs sold. And let's just say here that this is the price per pair. Let's keep that in mind. And now the cost will be the number of pairs sold, right? Right. And now we know that the numbers of pairs sold. So we know that the number is of $1 increases, right? So the number of pairs sold, right, is equal to 4,000 minus 400. And this guy, since the number of times here, okay, I'm going to write it like this. So this is the number of pairs sold times the price per pair, and the same goes here. Okay, price per pair. That makes more sense. So this would be times here the number of $1 increases. All right, let's call this variable x. So this would be the numbers of pairs sold will be nothing else than just 4,000 minus 400x, 400 times x. So the numbers of pairs sold is non-negative, that's clear. So since the number is non-negative, it follows that that 4,000 minus 400x is non-negative, which implies that x will be less or equal than 10. So the domain of the function will be, so the domain of our function, of the profit function, of p of x is all values of x between 0 and 10. So the function will be defined on 0 and 10. So now the profit, so the p of x will be nothing else than just 4,000 minus 400x times price per, okay, 5 plus x minus 4,000 minus 400x times 3. Right, and now we can, we know how this function would look like. Now we're going to do some algebra, and then we'll try to maximize this function. And then here where the derivative will come into play. So this would give us, if we do all this algebra here anyway, I'm just going to copy directly the computations. So this would be 400 after some algebra here, some computations exercise for you. So this would be 400 times 10 minus x times 2 plus x. So that's my function, the profit function. Look at it. It looks so nice. And now we would like to maximize this. So the maximum profit will be p prime of x is 400. And now we're going to take the derivative of this. So this would be negative 2 plus x. So we're going to apply the product rule here, plus 10 minus x. And this would be 400 times negative 2 negative x plus 10 minus x, which will give us, this would be nothing other than just 400 times 8 minus 2x. Or if you want, it's 800 times 4 minus x. Okay, so that's the derivative of this. And now guess what? We want to find a critical number. So we're going to set up this equal to 0. So the critical numbers, we're going to have just only one. So p prime of x is 0. If and only if 4 minus x is 0. So x is 4. So that's the critical number, this guy here. And now what we need to do is we want to evaluate our function p of x at the endpoints where of the domain of the definition, which is 0, 10. So we're going to evaluate now p of 0, which will be 400 times, let me look. Okay, it's here. For 100 times 10 times 2, which is 8,000. Now we're going to evaluate p of 10, which will give us 0. And now finally, p of 4 will give us nothing else than just 400 times 10 minus 4 times 2 plus 4, which will be 400 times 6 times 6, which is so it's 14,400, I think, yes. So the maximum profit will be $4,400. So the maximum profit is $4,400. Oh, that's quite nice. You see, you can optimize your business in this way. This is why calculus is nice. And now we would like to see the selling price. So the selling price of a pair of earrings is equal to 5 plus x, but x is 4, so it will be $9. Yes, and in this way you can maximize your profit. If you sell each pairing of earrings at $9, then you can maximize your profit, right? All right. I think that should be enough for today. I think I'm going to stop here. So this summarizes the chapter number 4, which, like I said, it involved additional applications of the derivative. Well, you have seen a bunch of stuff here. We talked about the extreme values of functions, about the mean value theorem. Also, we have talked about graph sketching, asymptotes, limits involving infinity, L'Hopital rule. We found out that there is another way of computing limits of functions in a very effective way, which involves derivatives. And now, today, in fact, we learned about how we can apply derivatives and moreover qualitative properties of derivatives in optimizing problems in physical sciences, business, engineering, economics, and so on. All right, guys, that's it. Next time we'll start chapter number 5. Thank you very much.